Let's get into chapter 2 then here. And in chapter 2, what we are going to get into are just some basic ideas and features and overall discussions of matter and energy. And so this particular part of the class focuses very, very heavily on kind of the physical science concepts that are going to drive a lot of what we talk about in the later parts of the semester. So these next couple of chapters are kind of physical science slash chemistry focused. But what they'll do ultimately is they'll give us some real insights into kind of the things that we need to know to better understand the hazards that are associated with certain kinds of substances. So we need to start with kind of the fundamental question here, and that is this: what is matter? Now, by definition, matter is anything that has a mass and takes up space. Now, mass itself is something that is related to weight. Weight is just simply the force of gravity on matter, pulling that matter toward the center of the earth. Volume is the fancy way of saying the amount of space that something takes up. And when it comes to matter itself, we tend to think of matter in a couple of different ways. We have these so-called physical states. And so with these physical states, the solid, the liquid, and the gas, this is one way of classifying matter. We can call it classification by phase. So there are differences between solids, liquids, and gases. The differences between them are relatively easy to look at. When we are talking about a solid, we're talking about some object that has a definitive volume and a definitive shape. That definitive volume and shape mean at the molecular level that we are going to see that the molecules are very close together and they are very organized in their pattern. So this organization, you can see all of these molecules are all lined up very nice and neat. They're packed very close together. Into what we would call a crystal structure. And you can see that rigidity that we find in solids is definitely related to this phenomenon, the fact that we have this kind of arrangement of those molecules. If we compare that to liquids, we can see that we still have this closeness in the arrangement. Look how close those molecules are together. But we are lacking that arrangement of those molecules three-dimensionally. Notice that we don't have those set lines. We don't have those very ordered kind of organizations. This molecule is not nearly as close to the other ones. And so as a result, it's able to move around much more freely than any of the solid molecules would be. So we call that disorganization or disordered arrangement. So even though we have this close together relationship, even though the interactions between the molecules are strong, this disorganization is going to be responsible for the lack of shape that we find in liquids. Liquids will always conform to the shape of their containers. And then finally, gases. Gases, we see considerable space between the molecules themselves. So from that end, we can't get a definitive volume because the spacing is far too far apart. And because there is no organization to this, we're not going to get a defined shape either. So that's the primary difference between solids, liquids, and gases. It all comes down to, at the molecular level, what do those molecules look like? How are they arranged? How do they react? How do they interact with each other? The more that they interact with each other, the more organized their structure is, the more rigid and solid-like they're going to be. The more disorganized they are, the more far apart their spacing is, the more gas-like they're going to be. And liquids kind of fall somewhere in the middle there. Now, there's one other way to classify substances. We can classify substances, that classification by composition, what we're doing there is we're looking at the overall makeup of the molecules. So pure substances are called so because they do not vary in their composition from sample to sample. So if I look at a particular sample of a pure substance, I am going to see that each one of those molecules look the same. So every atom or molecule is identical. That is what makes a pure substance a pure substance. Now, the two types of substances we can have that are qualifying as pure would be the elements, where we have one type of atom. And those would be things like what's on the periodic table of elements: gold, silver, sulfur, iron, oxygen, germanium, arsenic, and so on and so on and so forth. Compounds, on the other hand, would have two or more types of atoms in a fixed ratio. What do I mean by a fixed ratio? That I mean that the atoms that make up the molecules of compounds are always going to be of the same number and kind. So if I'm describing carbon dioxide, it is always CO2. If I'm describing sulfur trichloride, it is SCl3. If I'm describing sodium carbonate, it's Na2CO3. These compound formulas are consistent. They will always be the same thing. If I change it, then I change the very nature of the substance itself. If I go from carbon dioxide CO2 to carbon monoxide CO, even though it has carbon and oxygen in it, it's fundamentally different. Carbon monoxide and carbon dioxide are two different substances. They have two different sets of properties. So the fixed ratio part fits into this identical nature part that we're talking about with pure substances. So let's look at elements a little bit more closely. One of the defining features of elements is the fact that we cannot break it down into further substances. Now, we cannot do it with a chemical process or a physical process. There are ways to make elements break down into other elements, but they require nuclear reactions to do so. And so that really doesn't qualify as, what we're talking about here, breaking in simpler substances. When we do radioactive materials, well, guess what? That means that all the stuff that comes out of that's radioactive as well. It's not terribly useful to us to break down an atom, except for very specified purposes. There are 118 known elements. Those elements are ranged on the periodic table of elements. Those 118 elements are available in different types of varieties and in different abundances. So for example, oxygen is a very well-known and very abundant element here on planet Earth. In addition to making up just a little bit more than 20% of the atmosphere, it also makes up about half of the mass of the Earth's crust. So oxygen is a very prominent element. Elements like californium, CF, are man-made and only exist in laboratories and exist for very short windows of time in those laboratories. So their abundance is far, far less and far, far less stable. So of those 118 elements, there is a core group of about 30 elements that make up the majority of the things that we find here on planet Earth. Everything else, yes, they exist, but their quantities by comparison are in trace amounts or in small amounts comparatively. Compounds, on the other hand, again, keyword with compounds is this idea of a constant and definite proportion. That's what I was talking about, looking at carbon monoxide versus carbon dioxide. Changing the ratio of one element to the other changes the nature of the molecule itself. Now, we cannot break down compounds into simpler substances physically. So I can't simply boil a substance like water and expect to get hydrogen and oxygen out of it. But I can break it down by chemical or electrical means. We call those decomposition reactions. And there are a number of different ways that we can do it. Probably the one that you are the most familiar with is the electrical decomposition of water into hydrogen and oxygen, where you take water, you hook it up to some electrodes, and what you'll see is that at one electrode you start to form hydrogen, and at the other electrode you start to form oxygen once you turn on the juice. So compounds, because of this definite composition, this definite nature, is subject to something called the law of constant composition. The law of constant composition states that the elemental composition of a compound is always the same, regardless of the source of the substance or how much is present. So it doesn't matter if I have a thimbleful of water or the Atlantic Ocean. All of the water in those samples is the same. It's H2O. This idea of definite and constant proportions, this brings up another common law, fundamental law of chemistry. This is called the law of definite proportions. Where we can systematically define why compounds have a constant composition, why compounds have a fixed whole number ratio of one element to the other. That's what these two laws aim to determine. Now, on the other hand, we have mixtures. Mixtures are substances that have multiple substances in them, but each substance retains its own chemical identity. So what we can talk about here is this is a physical combination of substances, whereas we were talking about a chemical combination of substances when we talked about compounds. Now, mixtures can fall into two categories as well. There are the homogeneous mixtures, otherwise known as solutions. These mixtures have a uniform appearance. And because of their uniform appearance, they're often mistaken for compounds because compounds and elements also tend to have somewhat of a uniform appearance as well. The way that we can tell them apart is through separation. Homogeneous mixtures, because they are physical combinations of substances, we can boil off the water to find the salt that's left behind, or boil off the Gatorade and find the food coloring and the sugar and the other substances that are left behind in the Gatorade. Uniformity of appearance does actually mean that we can't see a difference we can't see the different components, but with some relatively simple techniques, we can actually separate them. Heterogeneous mixtures, on the other hand, have an ununiform appearance or a disuniform appearance. If you ever took a look at a sample of granite, you'll see all those different colored stones inside of the granite. If you ever look at sand, now sand is mostly silica, but you'll find little pebbles or seashells or other things in there. Take a big scoopful of the ocean water. You're going to get water, you're going to get sand, you're going to get seaweed, you're going to get microorganisms. You're going to be able to see each of those things as you go through. So that's the big difference between the two types of mixtures. It's about whether or not you can tell that there are multiple components present just by looking at it. Now, one way to help kind of keep our ideas straight is using a flow chart. And so if we can imagine matter, here's all of matter up here at the top. We can ask ourselves the question, does the matter that we are looking at have a uniform composition? If the answer to that question is yes, then we know that we are in the pure substances. If the answer to that question is no, then we know we're dealing with a mixture. On the pure substances side, the next question we can ask is how many different types of atoms? If the answer to that question is 1, then we're dealing with elements. If the answer is 2 or more, then we're dealing with compounds. On the mixture side, we can ask, okay, does it have a uniform appearance? If the answer is yes, then we know we're dealing with a homogeneous mixture or a solution. If the answer is no, then we're dealing with a heterogeneous mixture. So that's matter kind of in a nutshell. What we're trying to do is we're trying to figure out, okay, if I look at a substance, would I be able to determine whether or not it is an element or a compound, whether or not it's a mixture? And so a flowchart like this certainly helps with that. What also helps is just knowing those definitions and being able to apply them properly. Right. Any questions about matter before we move on to our next topic? All right, once again, I'll take that silence as a no. So let's go in and do some review questions just to kind of get an idea. So using the chat here, I want you to give me the answer to this first study question, A, B, C, or D. Which of these is not a pure substance? Water, carbon dioxide, carbon, or air? And if you think that there are multiple ones there, go ahead and put in multiple answers. All right, so the answer that we're all agreeing on here is D, the air. And we are correct. D, air, is not a pure substance, because inside of this substance of air, we would have things like nitrogen, oxygen, carbon dioxide, helium, and a whole bunch of others. So the fact that we have multiple substances in there, not just multiple elements, but multiple substances, would indicate that this is not a pure substance. Now, the only other answer that I saw brought up was carbon dioxide, and that one is incorrect. Carbon dioxide is CO2. The fact that it is always CO2 and does not have any other chemical formula would indicate that it is a pure substance. It just happens to be a compound instead of a mixture. Same thing for the water. Water is a pure substance. It is also a compound. Carbon, on the other hand, is just carbon, and it would be an element. All right, let's try another one. Solutions may be A, solids, B, liquids, C, gases, or D, all of the above. So we're pretty split on this one. 3 of you said it was liquids, 2 of you said it was all of them. Now, in the example that we gave you, we described solutions in the liquid phase. We talked about Gatorade, we talked about salt water, we talked about a whole bunch of things. All of them were kind of liquid-based solutions, and that's what we're most familiar with. However, on the last slide, we also talked about air. Air would be a good example of a gas-based solution. Because remember, all we're needing to be a solution is it needs to be a mixture and it needs to have a uniform appearance. Air certainly qualifies as both of those. So we have a gas phase mixture that is a solution in the form of air. Any combination of gases, in fact, would be a gas phase solution. Now for solids, it's a little bit more difficult to think about. Well, I'm going to give you a word here. Alloy. Alloys are examples of solid phase solutions. And there are 2 examples I gave you. If you combine copper and zinc in the correct kind of range of values, you would end up with brass. If you combine iron and carbon, along with some other things, you would get steel. If you throw zinc into that equation, you get galvanized steel. And if you look at any of those samples, they would certainly look uniform in their appearance. The reason being because you had to melt together those metals in order to get the combination. So we have examples of all three phases, and all three phases can make solutions. So the correct answer here is actually D, all of the above. All right, any questions with matter before we move on? All right, so the next thing that we want to talk about, we're gonna just take a brief introduction to it today, and we'll get more into it on Friday, is talking about units of measurement. So when it comes to units of measurement, there are two different types of units. There are what we call the base units of measurement, and these are kind of the simple units related to things like length, width, height, mass, force, so on. So for the base unit of length, we are talking about something called the meter. The meter is a little bit more than 3 feet long. It's about 39 and change inches. But in the metric system, a meter is equal to 100 centimeters or 1,000 millimeters. Kilometer is also a measure of length, and the kilometer is equal to 1,000 meters. And again, a kilometer is about 6/10 of a mile, a little bit more than that. So in terms of the metric system, the unit of measure that we kind of base everything on is the meter. For mass, the base unit of interest here is something called the gram. Now, a gram itself is not very much in terms of mass. And where we tend to go with it is if we're dealing with small quantities, we deal with milligrams, which are 1/1000th of a gram. Or if we're dealing with larger quantities, we can deal with the kilogram, which is about 1,000 grams. Now, a kilogram is about 2.2 pounds. Now, the key feature about mass is specifically the quantity of matter possessed by an object, regardless of its location. So ordinarily, when we measure things like mass, we have to take into consideration the gravity of the area around it. So, when you take your weight here on planet Earth versus your weight on the moon or on the planet Jupiter, it would change because the gravitational forces on each of those celestial bodies is different. But your mass would remain the same because you have the same amount of matter regardless of where you go. The base unit for volume is the liter, and that liter is just a little bit bigger than a quart. So it's like 30, 31 ounces. Again, a couple of things that we can pull from it. If we are dealing with cubic kinds of objects, a cubic meter is 1/1000th of a liter. But what we're going to do most often is we're going to go in milliliters. Milliliters, there are 1,000 milliliters in every liter. The exact conversion that we usually use, 1 quart, which is 32 fluid ounces, is equal to 946 milliliters. Volume is all about capacity. How much stuff can we fit in a particular tank or a particular container? As you can see, units of length and distance can be used to give other ideas. So if I took just simply length times width, I'd be able to determine the area of a face of this cube. If I took length times width times height, I'd be able to get all three dimensions. This would be a volume conversion. And 1 cubic meter, as we mentioned before, is equal to 1,000 liters. So a cubic meter is actually pretty big. And this is just showing that if you broke up each cubic liter, so if I was looking at just 1 liter, notice that the dimensions of the box have changed. It's now 10 centimeters in each direction. So 1 liter is equal to 1,000 milliliters, or 1,000 cubic centimeters. Now, the metric system has not been something that has been very well used or well documented here in the United States. Generally speaking, other than in the scientific community, we largely still don't use the metric system other than in some real specific circumstances, for things like imported vehicles, or some other transportation related kinds of things. The US did not actually reach full adoption of the metric system for certain kinds of things until 1988. This was the Omnibus Trade and Competitiveness Act. And where this what this forced was it forced certain building and highway construction companies to begin using the metric system. Some places took it further than others. There are a couple of places actually where you can go through. There's certain parts of Kentucky, as well as other places throughout the country, where you can see road signs that instead of having mile markers showing you, okay, Bowling Green, Kentucky is 40 miles away, it'll actually give the value in kilometers. But that's really as far as the extent of that kind of thing has come into our everyday focus. For the most part, we still use the customary system, otherwise known as the English system. That system invokes inches and feet, fluid ounces, those kinds of things, instead of liters and grams and meters. Now, our primary topic on Friday will be this: how do we convert between units? So let's say that I need to do a conversion between meters and centimeters. How do I go about doing that? Well, that's where the factor unit method is going to come in. In the factor unit method, we need to identify our desired unit, which in this case would be the centimeters. We need to choose the proper conversion factor. So this is something that we would have to look up. There are 100 centimeters in a meter. And then we'd have to apply that conversion factor correctly so that we ended up canceling out the units that we needed to cancel out. So let's just say, for the sake of argument, we are going to convert 17 meters into centimeters. Well, I would start with my 17 meters. I would need to use my conversion factor as a fraction. So since I have meters in the numerator here, I would want meters in the denominator there to cancel it out. Now we put centimeters up top, and then I would need to drag over the numbers 100 centimeters in 1 meter. That would make my meters cancel. I'd be left with the centimeters. And I would just need to do the multiplication. 17 times 100 would be 1,700. My meters canceled, so the units would be centimeters. So that is going to be the topic for our discussion on Friday, is doing more with these kinds of calculations and conversions. But I'm going to leave it right there for right now.